Now that our machine learning environment is prepared, we are ready to study our first machine learning algorithm, which is linear regression. Linear regression is one of the simplest yet most powerful algorithms in machine learning. It belongs to the family of supervised learning algorithms, specifically designed for regression tasks where the goal is to predict a continuous numerical value. In many real-world problems, we want to understand the relationship between variables. For example, predicting house prices based on house size, predicting salary based on years of experience, predicting electricity demand based on temperature, predicting exam scores based on study hours, etc. Linear regression attempts to model these relationships using a linear mathematical function. The main idea behind linear regression is simple. If two variables are related, we can approximate their relationship with a straight line. For instance, suppose we collect data showing the relationship between study hours and exam scores. When we plot this data, we may notice a general upward trend. Students who study more tend to score higher. Linear regression attempts to find the best fitting straight line that represents this relationship. Once the model learns this relationship, it can predict future values. For example, if the model learns the relationship between study hours and exam scores, it can predict the score of a student who studies for a certain number of hours. Despite its simplicity, linear regression remains widely used because it is easy to interpret, computationally efficient, and surprisingly effective for many real-world problems. The mathematical foundation of linear regression is based on a simple equation that represents a straight line, that is y equal to mx plus b. Now let us understand what each component of this equation represents. The variable x represents the independent variable, also known as the input feature. This is the variable that we use to make predictions. The variable y represents the dependent variable, which is the value we want to predict. The parameter m represents the slope of the line, and the slope determines how much the predicted value changes when the input variable changes. For example, if the slope is positive, it means that as the input increases, the predicted value also increases. The parameter b represents the intercept, which is the value of y when x is equal to 0. In machine learning, the goal of linear regression is to find the values of m and b that best fit the data. This is usually done by minimizing the prediction error between the actual values and the predicted values. A commonly used technique for this purpose is least squares optimization, which finds the line that minimizes the square difference between predicted and actual values. Although this equation looks simple, it forms the basis for many more advanced machine learning models. In linear regression, the behavior of the model is determined by its parameters. The two key parameters are the slope and the intercept. Let us first discuss the slope. The slope represents the rate at which the dependent variable changes when the independent variable changes. For example, suppose we are predicting house prices based on house size. If the slope is large, it means that a small increase in house size results in a significant increase in price. If the slope is small, the relationship between size and price is weaker. The slope therefore captures the strength of the relationship between variables. Next, we have intercept. The intercept represents the predicted value when the input variable is 0. In many real-world situations, the intercept may not have a direct physical interpretation, but it still plays an important role in defining the regression line. For example, if we are predicting salary based on years of experience, the intercept represents the predicted salary when experience is 0. Machine learning algorithms estimate these parameters automatically during the training process. Once the parameters are learned, the regression model becomes a mathematical function that can generate predictions. Understanding these parameters is important because it allows us to interpret the model and understand the relationship between variables. Before training any machine learning model, we must first load and explore the dataset. Data exploration is a crucial step because it helps us understand the structure and characteristics of the data. The first step is reading the dataset. In Python, datasets are commonly stored in files such as CSV files, Excel spreadsheets, or database tables. Using the pandas library, we can simply load a dataset into a data frame. Once the dataset is loaded, the next step is data exploration. This involves examining the dataset to understand the number of rows and columns, the data types of each variable, whether there are missing values, and whether there are unusual patterns. Pandas provides functions such as head function to view the first few rows, info function to see the structure of the dataset, describe function to view summary statistics, etc. These functions help us understand the dataset before applying machine learning models. Another important step is summary statistics. Summary statistics include measures such as mean, median, standard deviations, minimum and maximum values, etc. These statistics provide insights into the distribution of the data and help identify potential issues such as outliers. Exploring the dataset carefully ensures that we understand the data before training models. After loading the dataset, the next step is data cleaning and preparation. Our data is rarely perfect. It often contains missing values, inconsistent entries, and unusual observations. The first issue we usually encounter is missing values. Missing values occur when certain data points are incomplete. For example, in a housing dataset, the number of bedrooms for some houses may be missing. Several strategies can be used to handle missing values. We may remove rows containing missing values or replace missing values with the mean or median, use predictive techniques to estimate missing values. Now, another important task is detecting outliers. Outliers are extreme values that differ significantly from the rest of the data. For example, if most houses cost between 100K and 500K, but one entry shows a piece of $10 million, it may indicate an error or an unusual observation. Outliers can distort machine learning models, so they must be handled carefully. The final step in preparation is feature scaling. Feature scaling ensures that all variables operate within a similar numerical range. For example, if one feature ranges from 1 to 10 while another ranges from 1 to 100K, the larger feature may dominate the model. So scaling techniques such as normalization or standardization are used to ensure that features contribute equally to the model. Now, proper data cleaning and preparation significantly improve the performance and stability of machine learning models. Once the dataset is cleaned and prepared, the next step is feature selection. Feature selection involves identifying which variables are most useful for predicting the target variable. In many datasets, some features may have little or no influence on the outcome. Including unnecessary features can lead to increased computational cost, reduced model accuracy, and overfitting. Therefore, selecting the most relevant features is an important step in building an effective model. One common method for feature selection is correlation analysis. Correlation measures how strongly two variables are related. For example, house size may have a strong positive correlation with house price. If a feature shows very weak correlation with the target variable, it may not contribute much to prediction. Another method is feature importance analysis. Some machine learning algorithms, such as decision trees, automatically estimate how important each feature is for making predictions. Features with very low importance scores can sometimes be removed. Feature selection helps simplify the model while improving performance. It also makes the model easier to interpret and understand. Now that the data is prepared and the features are selected, we are ready to train our first machine learning model. The first step is splitting the dataset. Typically, the dataset is divided into two main parts, the training set and the testing set. The training set is used to teach the model how the input variables relate to the target variable. The testing set is used to evaluate how well the model performs on unseen data. This separation ensures that the model does not simply memorize the training data. After splitting the dataset, the next step is fitting the model. During training, the algorithm analyzes the training data and learns the best parameter values. For linear regression, this means finding the slope and intercept that minimize prediction error. Once the model has been trained, it can generate predictions for new inputs. For example, if we trained a model to predict house prices, we can input the features of a new house and obtain a predicted price. Training the first model is an exciting step because it demonstrates how data can be transformed into predictive insights. After training the model, we must evaluate its performance. Model evaluation determines whether the model is accurate and reliable. For regression problems such as linear regression, two common evaluation matrices are used. The first matrix is mean squared error. Mean squared error measures the average squared difference between the predicted values and the actual values. If the predicted values are very close to the true values, the mean squared error will be small. A large mean squared error indicates that the model's predictions are far from the true values. The second matrix is R squared, also known as the coefficient of determination. R squared measures how well the model explains the variation in the data. Its value ranges between 0 and 1. An R squared value close to 1 means the model explains most of the variability in the data. An R squared value close to 0 means the model explains very little. Together, these matrices help determine whether the model is performing well or needs improvement. The final step in this section is interpreting the results of the model. Building a machine learning model is not only about generating predictions, it is also about understanding what the model has learned. One important aspect of interpretation is examining the coefficients of the model. In linear regression, each feature has a coefficient that indicates its influence on the predicted value. For example, if the coefficient for house size is large and positive, it means that larger houses tend to have higher prices. If the correlation for age of the house is negative, it means older houses tend to have lower prices. These coefficients help us understand the relationships between variables. Another important concept is residual analysis. Residuals represent the difference between actual values and predicted values. By analyzing residuals, we can determine whether the model is making systematic errors. For example, if residuals show a clear pattern, it may indicate that the model is missing important relationships in the data. Residual analysis therefore helps identify opportunities to improve the model. Through careful interpretation of results, we can gain valuable insights into both the data and the model's behavior. And that's all for this video.